Hi everyone, Ollie here. Thank you for joining me on Hyperfocus, where we dare to push science far beyond the usual pop explanations. I want to talk about quantum tunneling, but hold on. This won't be your everyday electron sneaks through a wall story. By the final stretch, we'll push into advanced quantum gravity territory, so please, brace yourself. Let's start gently. Quantum tunneling is the weird scenario where a particle, which classically shouldn't have enough energy to overcome a barrier, nonetheless appears on the other side. Picture standing at a locked door, lacking the strength to barge through, yet you somehow end up inside the room. Classical physics says that's nonsense. Quantum mechanics says, actually it can happen. This phenomenon is crucial for alpha decay in nuclear physics, explaining how an alpha particle leaks out of a nucleus. If it weren't for tunneling, processes fueling our sun would be drastically diminished. Our daily sunshine? Partly courtesy of quantum smugglers. Alright, so that's the baseline. But let's tiptoe into the intermediate zone. How do we represent tunneling mathematically? Typically, we use the WKB approximation, named after Wenzel, Kramers, and Brillouin. In one dimension, the wave function psi of x can be approximated by exponential functions that either blow up or decay in classically forbidden regions. Here's the idea in words. The wave function can be expressed as an exponential with a factor that depends on the difference between the potential energy, v of x, and the particle's energy, e. If v of x is bigger than e, that factor causes the wave function to decay. This effectively lets the wave function tunnel through a region, even though it shouldn't have enough energy, classically speaking. Sure, it typically decays quickly, meaning the tunneling probability is small, but it's never strictly zero. That alone is mind-bending. But let's see how it weaves into everyday electronics. In semiconductor devices, especially tunnel diodes, electron tunneling is harnessed for fast switching or specialized conduction. Meanwhile, engineers designing ultra-dense transistors face the dreaded problem that electrons can just quantum tunnel across ultra-thin gates, causing leakage currents. So ironically, we rely on tunneling for advanced hardware, but it also becomes a technical headache. Welcome to the dual nature of quantum phenomena. Now, if that's not enough, quantum tunneling also powers potential breakthroughs in quantum computing. Qubits can take advantage of phenomena like superposition, entanglement, and yes, tunneling, to explore vast solution spaces in parallel. Maybe one day, quantum processors will harness controlled tunneling pathways for faster logic gates. We're not there yet, but labs worldwide are exploring everything from superconducting qubits to topological qubits to reduce errors and harness quantum resources. All right, it's time. You know me. I'm unsatisfied if we just linger in the comfortable zone. So let's really push the envelope into controversies that tie quantum tunneling to quantum gravity and the very structure of space-time. You ready? One advanced direction arises from the hartle-hawking no-boundary proposal, which suggests the early universe may have tunneled from a quantum foam-like state into classical expansion. It's reminiscent of a boundaryless geometry that transitions into inflation. Formally, theorists consider a path integral over different four-dimensional geometries, weighted by the Einstein-Hilbert action, checking whether certain configurations tunnel from a pre-geometric realm. Without that quantum leap, maybe there'd be no Big Bang singularity resolution, just emptiness. Speculative? Yes, but it's one of those frontiers bridging quantum field theory, general relativity, and cosmology. We can push that further by considering string cosmology. The idea is that extra dimensions, like those in a Calabi-Yau manifold, could occasionally undergo tunneling transitions between different vacua, effectively toggling the shape of those hidden dimensions. Each shape or flux configuration can yield distinct particle physics. So perhaps the reason we see our local version of laws is because the universe settled on a certain compactification via quantum tunneling. There's even talk about the string theory landscape containing an enormous multiverse of possible vacua, with the universe quantum leaping from one to another in its earliest epochs. And yes, let's not forget black holes. A big question is whether black holes can let a particle tunnel out across the event horizon, a phenomenon related to Hawking radiation. Mathematically, we describe a field near the horizon with modes that can quantum tunnel outward, appearing as thermal emission. Some hypothesize more radical ideas. Maybe the entire black hole evaporation can be viewed as a huge tunneling event over cosmic timescales, bridging states inside the horizon with external states in the wider universe. Then you have the firewall debate. Do infalling observers see a calm horizon, or do quantum effects create a searing barrier? The role of tunneling, whether it spares the horizon from a destructive firewall or enforces it, remains hotly contested. If we incorporate stringy fuzzball models, we might treat the horizon as an ensemble of quantum microstates, each enabling some measure of tunneling-like behavior. In short, this is an open question, and the advanced theoretical physics world is still grappling. Now, philosophy fans, does quantum tunneling shatter determinism? If fundamental events rely on probability amplitudes, can we speak of absolute cause and effect? Some interpretations emphasize wave function collapse under measurement. Others champion many worlds, positing that tunneling is just a branch split in the universal wave function. Meanwhile, relational interpretations question whether the barrier even has a fixed property of impassibility, or if that's observer-dependent. Tunneling, in that sense, defies a single true narrative, aligning more with probability distributions than Newtonian laws. Zooming out, it's amazing how this quantum riddle, initially describing radioactive decay or electron transitions, might shape the fate of black holes, the early cosmos, or the existence of entire vacuum states. Indeed, the moral of the story is that boundaries in quantum physics are not as rigid as we once believed. A locked door might simply be an invitation for wave functions to do their improbable dance. So let me ask you, does quantum tunneling prove that reality is fundamentally leaky, even at the grand cosmic level? Or do we simply not yet grasp the full tapestry of quantum gravity that might unify these bizarre observations into a cleaner picture? Please let me know your thoughts below, especially if you've got your own angle on black hole horizons, string cosmology, or advanced quantum computing. Remember, this channel is brand new, so your input truly shapes where we dive next. Stay cruised, stay hyper-focused, and keep tunneling through every barrier that tries to confine your curiosity. Until next time.